Let's say you started out with a three-dimensional body, and just for generality, we take it to be three-dimensional. It can be any dimensions, 1, 2, 3, whatever you have. And let's take an axis. So whether through it, whether away from it, let's take this axis. And with respect to this axis, even though it's sort of oblique, but anyways, if you rotate this body with, let's say, a constant angular velocity of omega, then what that means is that in 1 second, this body rotates by omega radians. So if this were 2 pi, if omega were to be 2 pi, then in every second, this body completes a complete revolution. So 2 pi radians, 360 degrees represents that. Now, what that means is on a molecular level, each particle, so let's say this particle P right here, which lies at a distance of, this is perpendicular distance by the way, it lies at perpendicular distance of RP from the axis. If you look at it from the top, so if you were to put your eye here and you look at it from here, the body, let's say this were your body, let me do that in green. So if this were your body and it was doing all sorts of crazy motion and this were your axis pointing out, and this body would be doing all sorts of complex motion, but this point P right here, if you looked at it from the top, then this would look as if it's going in a pretty great circle that is centered about that axis, that is centered about the point that is here, and it has a radius of r sub p. And since this particle goes on in an angular velocity of omega, what you can write is that the velocity, the perpendicular velocity v is going to be r sub p times omega. And what that just means for us is that we know what is the exact velocity of every point with respect to this axis, if you take this omega angular velocity. And similarly, you can extend this for any particle you want. So if there were a particle here, let's say q, and then the distance of q from this axis, now notice you don't take this distance again from this point right here. This is just simply wrong. Now, this q rotates about, again, a perpendicular distance from the axis, so the shortest distance to the axis. Let's say this time it's at this point, and again, q would in fact rotate in some circle. Let's say that circle's radius is r sub q, and similarly, you can go on for infinite particles if you have. So in general, what my goal of the video is to find the kinetic energy of rotating bodies. So if you had, let's say in this chart, let's say you had an axis and you had two masses. Now this axis can also pass through these masses. It doesn't really matter. So if, let's say, you had 2 point masses at different distances, so if they were connected like this, the axis, like, I'm just generalizing it, then if this distance was r1, this was m1, and this distance was r2 here, this perpendicular distance was r2 here, and then this entire system is rotated with a constant angular velocity, then for the m1 particle, if you look at it from the top, if this were your axis, then m1 rotates about this axis, completes a circle that has a radius r1. It has a velocity of r sub 1 omega, and thus the kinetic energy of mass 1 is equal to half m1 times the velocity squared. Now the velocity, we know it's omega r1, so half m1 times omega r1 squared. You can similarly write this for the second one, for the second mass that you have. So the kinetic energy of mass 2 is equal to half m2 omega r2 squared. Now, the kinetic energy of this entire rotating body, assuming that this this rod is relatively light, negligible compared to these masses, you can write that the entire rotating apparatus that you have, the entire rotating body, has a total kinetic energy of half m1 times omega squared r1 squared plus m2 times omega squared r2 squared. Take omega squared common in this. This would get you half omega squared m1 r1 squared plus m2 r2 squared. And there you go. So if you know the masses, if you know the perpendicular distances, you can always find the kinetic energy of a rotating body. Let's say you wanted to extend this. Let's say you wanted to add one more particle right here. Let's say R3 came in right here, and it has a perpendicular distance. So let's say it was connected somehow like this, forming sort of a triangle. And this had a perpendicular distance of R3, M3 at a perpendicular distance of R3. What you just need to do is you need to include an M3 R3 squared component here. And be my guest, go over the computation again, and you would just arrive at this. In this manner, you can add on as many as particles you want. And the goal in doing so will be to create an infinite array of such particles. So in particle, 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 everywhere there is a particle, which has negligible mass. So a single particle might have just mass of dm. So an infinitesimally small mass dm, approximately 0. But when all of these add up, let's say they give you this big body, and that big body, just like we had one right here, this is actually composed of those many particles. So what that means is that in general, since half omega squared is not going anywhere, you would write that kinetic energy is equal to half omega squared times, well, we can always write the sum of mass times the radius, the perpendicular distance squared, the sum of all of that. So from I equals 1 for the first particle till the nth particle. But then if this is for a discrete system wherein there are clear boundaries between the first and the second and the third and so on till the nth particle. If you had let me just write discrete particles. And if you had a continuous body, then these mi's are replaced by dm's, and since you are doing a summation over infinitely many things, you take an integral, and then this r squared just remains the same, but now this is the r squared of that body. So the integral of dm r squared times half omega squared, this is the kinetic energy of a rotating body. This rather seems a bit ambiguous, since the integral of dm times r squared, that really would not have made any sense to you if you are visiting this for the first time. However, what this represents, notice, is that let's just take the discrete example first. If one of these r's would have been bigger, would have been bigger, then the kinetic energy at an angular velocity omega would have been bigger than it would have been for a lower mass. And similarly, if you would be having a bigger mass, then you would again have a bigger kinetic energy. If you had a translating object though, so let me just write it right here. If you had a translating object, it has a kinetic energy of half v squared times the total mass. So the total mass, let me just write that in integral form, that is just the sum of all the dm's, all these small tinsy-binsy particles right here. And the only difference between these two, well, first obviously is the difference between angular velocity and linear velocity. But the difference between these two is, this is the mass. Mass is an inertial property. So the more mass something has, we say it has more inertia to move, to do translatory motion. If a body has more of this integral stuff, we again say this has more inertia. This thing's termed as the moment of inertia. simply because a rotating body having a bigger weightage to it, a bigger moment of inertia to it, will have a bigger kinetic energy. So the trouble that we had in moving a particle rectilinearly, in moving a particle through a translatory motion, was the mass. Right now it's the moment of inertia. Now this idea of this moment of inertia as a physical concept is something that we'll continue developing in the future videos. For now, you can just take my word and just note moment of inertias for some common bodies until we get to a point where we can derive them on our own. So a moment of inertia of a rod having mass m and having length l, if you wanted to rotate it from a perpendicular axis perpendicular to it, passing through its midpoint, then the moment of inertia in that case, if you do the integral, and that's something we will obviously do, this comes out to be 1 over 12 ml squared. Now this is just to give you a feel of the numbers. You really will get to put this in your head in later videos. And moment of inertia is denoted by I, as I just wrote here. So the kinetic energy of this rotating body, not just a rod, any rotating body in general, is equal to half I times omega squared. I is the moment of inertia and omega is the angular velocity. When we go to talk about motions that involve both translation and rotation, we will include both of these. We would include both of these kinetic energies, and it's just so much fun to study physics of these kinds of objects. See you in the next videos.